Okay, welcome back. Today we are going to continue our C tutorials and we are going to start talking about basic binary numbers. They're very important to what we do with the pokeemerald decomps because the GBA, it has all of its, addresses and all of its variables actually stored as binary. At the end of the day, that's what they get converted into. So a lot of the time we have to work directly with those bits to change flags and things like that that are set in the game to do different things. So understanding how binary works is a little bit important. So binary numbers are not that complicated. They're some would say even less complicated than the decimal number system that we use for most of our math that we learn throughout school, the system based on 10. So in our system, each place in a number, if you wrote the number 123, the first place is the ones place. The second place is the tens place. The third place is the hundredths place, and so on and so on. But what this really is this first place is the 10 to the 0th place, which is 1. So this is 3 times 10 to the 0, plus 2 times 10 to the first. 10 to the first is 10. This is the 10th place, plus 2 times 10 to the first, plus 1 times 10 to the second. 10 to the second is 100. This is the 100th place in 123. So 1 times 10 to the 100 plus 2 times 10, or times 10 to the 1 plus 10 squared times 2 plus 2 times 10 to the first plus 3 times 10 to the 0th is how we get 123, the actual value on our number system based around the number 10. Binary works in exactly the same way, but it's based on the number 2. So instead of having 0, 1, 2, 3, 4, all of those numbers up to 10 inside of the place, instead of being able to choose any of those values, we can only choose 0 and 1, because when we get to 2, it now goes over to the next place, because this is 2 to the 0th. 2 to the 0th, it's either on or off. Either we don't have something in that place or we do, and that's 2 to the 0th times whatever's in this place. So for this example, it's 0. So 0 times 0, 0 times 1 is 0. This whole thing is 0. All of these places are 0. But for this one, we have this 1 here. So this is 1 times 2 to the 0th. 2 to the 0th is 1, so 1 times 1 is 1. So this is the binary number for 1. It's just 1. You could cut all of this off and it would still be 1. But if we're representing it as an 8-bit variable, or also known as a byte, 8 bits is a byte, and a bit is a 1 or a 0. So if we're representing it as a whole byte, we'd have all these zeros here, but also just 1 on its own is just 1 in binary. Now, if we wanted to represent the number 2, 2 is 2 to the first, so we have a 1 in the 2 to the first place, and that is equal 2 to the first times 1 plus 2 to the 0th times 0 is just 2, because 2 to the 0th times 0 is 0. So the same thing is true for the 4th place. That's just the 2 squared. Here is the 2 to the 3rd. Here's 2 to the 4th. Here's 2 to the 5th. Here's 2 to the 6th. So if we wanted to get 68, 68 is 64 plus 4. 64 is 2 to the 8, or 64 is 2 to the 6. 1, 0, 1, 2, 3, 4, 5, 6. And then 2 to the to get 4, we just do 2 squared. So it's 2 squared plus 2 to the 6, and those are the ones that we put inside of the binary number to get out 68. For an 8-bit binary number, we can go up to 255, because the next place is 2 to the 8th, because we start at 0 again. 2 to the 0th, 2 to the 1, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 5th, 6th, 7th, and an 8th. And 2 to the 8th is 256, so we can store up to 1 less than that, because we can't fit that bit because that bit doesn't exist here because we're only working in 8 bits. If you're working in 16 bits, a 2 byte, you can store up to 65,000, assuming we're working in, these are unsigned, so these are just positive numbers. We can also, if we wanted to, we could cut off this last bit and we could treat it as a 7-bit integer, but this last bit would be if it's 0, it's positive, if it's 1, it's negative, or vice versa, and that's how we could have a signed integer stored in a binary value. So that's the basic understanding of how the binary system works and how it compares to our decimal system. So it's important because sometimes when we're working on an embedded system like the GBA, we have constraints that we have to fit within with memory, and sometimes that means working on the bit level instead of being able to take advantage of whole swaths of space. We want to store as many things as we can as tightly together, especially when we're working with things like the save files. If we want to maintain our save compatibility across our releases and with other Pokemon games, there are some complicated things you have to do to make sure that the save block doesn't get edited, and we have to take advantages of extra bits here and there for things like that. So we are going to get into how to actually look at and compare and assign binary values in C. So to start with, a lot of the time we use in regular C, not necessarily in pokeemerald, we use chars as binary values, 8-bit values specifically, because they are 8 bits, but we can also do all these bitwise operators we're about to talk about using integers as well. U8s, we can do them with those as well. So to define, a binary value and initialize it with 0, we just define this char with 0 as the char value, because 0 is 0 in binary. That is what it's assigned to. So we know that this flags is just 0, 0, 0, 0, 0 all the way across. It's this 8-bit value here. We have all of these bitwise operators here that we can use in our conditionals these ones here that we can use in our conditionals, and also in our assignments to do different things. They're the same as the conditional operators in regular C that we used, except at least these two are, we only use one of them instead of two. Before and was two and symbols, but the bitwise and is just one. And what this does is it takes two binary numbers, let's say the 4 and the 68, and it ands them together. Anding a binary number goes through each individual place, and it does a binary and, a bitwise and. 0, 0, neither of these are 1, so the and value is 0, obviously. 0, 1, 1 and 0, well, that's true and false, so that's false, so that's 0. 0, 0, 0, well, here, 1 and 1, 1 and 1 is true, so we get a true, and then 0, 0. So the and of 4 and 68 actually ends up just being 4, because that's the only one that they share. They both have to be on for and. If one is on and the other is off, it doesn't fall through. So if we're using this in an if statement, if flags and if this binary and this binary number, well, it'll give us this one. This one is 4 equivalent. That, as we know, has a Boolean value. It's a truth value because it's not 0. So it would only give us false if we had zeros all the way through after the and was completed. So that would run the code down here because this is a true value if we did it on these two binary numbers. We can also do the same thing with or. Or would include if it was a 1 and a 0 like this. So it would or would give us 68. Between 4 and 68, if we OR these together, we would get 68. Now, if we used this one is the exclusive OR, this caret, it would give us something similar, but instead of, it would give us this, because the exclusive OR are the numbers that are from one, that are on in one but not the other. So if we were doing 4 and 68 together, this one is off, this one is on because there's a 1 here but not here. Then we go through off, off, off. This is off as well because the 1 is here and here, so it's not exclusive. So this would be off, this would be off, this would be off. So it would be like this. And this would just be the number 64 at this point. Because we know that this is the 2 to the 6th place, and 2 to the 6 is 64. So that is how these bitwise operators work here, as well as the tilde. This is the negate, and this just flips all of the bits in a binary number. So this 0, 0, 0, this number here will become 1, 0, 1, 1, 1, 1, 1, 1. And that will just be 255 minus 64. But this is what the not of this is, of this number is this, because we're just flipping each individual bit. Now to get to the shifts take a number, a bitwise number. They can also be just, a regular integer if we want here, because again, this 1, well, they can't be a regular integer, but they, this 1, it'll take this, it'll interpret it as a binary value, and then it'll shift it 4 to the left. And we can also shift to the right as well. So if you want a visual interpretation, if we were to shift this number 1 to the left, we would just move the 1 over. If we were to shift it 2 instead, then we would have gotten this. So it would take the 1 that was here and it would shift it 2 over. If we wanted to shift it 4, which is what this is doing, because this is just the binary number for 1, it took this 1 that was here and it shifted it over 1, 2, 3, 4, shifted over 4. This one shifted over 7. So these, we can use these constants here, the defines, if we want to. You don't have to. There are other ways to declare it, obviously, like here. But a common way of defining flag masks and things like that is to use a constant. So we have defined this constant by shifting the bitwise value over, and that way it makes it easier so you don't have to remember what the value, because otherwise if you're setting this, you need to set this to 0x and then generally the hexadecimal value. You could also set it to the actual, how I set it to 0. You could set it to whatever the char equivalent is, or the int equivalent if you're using an integer. But here you don't have to know what the conversion is. You just need to know the space, the positioning of your flag, and that's sometimes all that's really going to matter, because the number itself isn't what you're worrying about. It's just the position, because you're just storing a flag in this spot, on or off. I'm saving this value here from something else, like if you had done something in the overworld and you wanted it to save and reload every time in that way, you would have to have a flag for it. And if you were adding flags and needed space and wanted to hide one somewhere at the end of a struct, say with some unused space, you would want to have a mask for the flag so that you could check to see if it was there, and that's basically what we do here. We are checking the flag to see if it's in this spot. So if we were hiding something here, we would check the flag that we would put here, and then we would run code. Now, how we actually assign flags, we use the OR equals to, which basically because of how OR works, it just adds, no matter what's in this one, if we're ORing this into it, this is going to stay, but it's just going to take whatever is extra from here. So if I add some extra bits in here, if I'm ORing these two numbers together, it's just going to take all of the stuff from both. So if I have a flag here, and I have, you know, a list of flags here, and I want to add this flag here, I can just OR them together, and then no matter what's in this, all it's going to do is add this one if it's not there already. If it's there already, it's not going to do anything. It's just going to stay the same, because it's OR, not exclusive OR. So OR, it doesn't matter if they're both there, because it's not exclusive OR, it's just regular OR. So if you want to assign a flag into a list of flags, you would, you know, create the, you know, a binary representation of the flag that you want to set, and then you would set it with the bitwise assignment. And to clear the bit, you do a very similar thing, but you need to AND equals the knotted flag. Now, how this works is, let's say we have we have right here, here's our list of flags right here, and here is our, this is going to be flags, and this is our flag 1. We also have the not flag 1, which is 0, 1, 1, 1, 1, 1, 1. So how this works is we are ANDing equals, so this is going to end up with the AND. It's going to be the result of the AND of flags and not flag 1. So it's going to be the AND of flags and not flag 1 is going to be what we're going to assign into flags after we're done with the AND. So the reason why we not it is because that is how we ensure that this binary number, the not flag 1, it has every single value ANDed except the one we are trying to remove. It has every single value added except the one we're trying to remove. Because when we're ANDing that way, no matter what is ANDed with this, it's going to include all of the values that are on this part of the flag, all of this values that are on part of this part of the binary number. It's going to include them all no matter what, because this is 1 all the way across. So as long as there's a 1 here, it's going to fall through to the final variable. But here, where our flag is, the flag we're trying to clear, is always going to be a 0. So it can never be ANDed with the 1. It will never fall through because this is always 0, because it's knotted when it was a 1. It's always 0. It's not going to fall through. So that way that the flag is cleared when we AND equals it, because an AND with a 0 is a 0. So that way with the not, we are able to clear a bit with the AND equals and knotting a flag. So those are our operators, our basic operators with binary numbers. There are some more complicated stuff, but we are going to now talk about hexadecimal. So we just talked about the difference between the decimal system and the binary system, how it's using 2 versus the number 10 as a base. Well, the hexadecimal system it works in the exact same way, except we are now using 16 as our base. And we do this because it's really easy to represent a 8-bit or a 16-bit or a 32-bit binary number in hexadecimal, because the 8 bits can be broken up into 2 4-bit sections, and those 4-bit sections, because of the relationship between binary and hexadecimal, can just be represented as 2 side-by-side hexadecimal numbers, one place hexadecimal numbers. Each 4-bit binary number is represented by 1. So if we have a larger binary number, we can represent it as 2 conjoined hexadecimal numbers, and it's the same thing. It's the same value equivalently in the hexadecimal system. So hexadecimal, obviously, because we're going up to 16, our normal numbers are not enough. Our normal numbers only go up to 10 because our binary, only go up to 9 because our binary system is based on, or our decimal system is based on that you know, like our numbering system is based on our decimal system. Sorry. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 because we're on a 10 base system with our general mathematics. So we need new numbers to go up to 16 or 15 technically, because 16 is when it loops back around, just like 10 is when it loops back around. So we use letters. We use A, B, C, D, E, F. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So they're exactly the same as you know, the normal numbers that we use. There's no difference to them. It's just what they're representing their value is at the end of the day, compared to our base 10 system. F is 15 in our base 10 system, but in hexadecimal, F is just F. Like, that's just it. It's F. It's not 16, or it's not 15. It's just F. It is 15, but that's just when we convert it into our system that is easier to understand for our brains because it's what we've used since school. So anyway, we are going to, I have a shortened table. I cut off some of it, so it should keep going down here and then wrap up to here. But this is the binary 0, 1, 2, 3, 4, and these are just 4-bit numbers. They're not 8-bit numbers, so these are more separated. And then these are the hexadecimal representations for these binary numbers. So 0 is 0x0, 1 is 0x1, etc. down, and we get to 8, 9, but then we go to, this is 10 here, because this is the 2 to the first spot and the 2 to the third spot, which is 8 plus 2 is 10. So 10 is 0xa. And that's, you know, exactly what we said here when we were going through up to 9 and then 10. And then this is 11, B, 12, C, etc., all the way down with the different binary representation. So if we were to take a 8-bit binary number and we wanted to represent it in hexadecimal, we would just separate its bits, its 4-bit sections, and we would say, well, 1, 0, 1, 1, that's here, and that's B, so that's this part, and then 0, 0, 1, 1 is here, and that's 2, so that's the first part. So this number is 0x2b, and it happens to be 43. That's just what this whole 8-bit value is equal to. So that is how we represent basic binary numbers using hexadecimal, and this is kind of important because a lot of the time things like memory addresses, they're not in integer, they're not in decimal or binary. A lot of the time they're in hexadecimal. Is how we represent them, because a lot of the time we are representing things by byte, and it makes it useful in that way. Now, there is something to note about hexadecimal representation, especially when we're talking about memory addresses instead of values. When we're representing a hexadecimal value, a whole 2-byte value like this is this value in this order. You start, you know, from 3. 3 is 16th to the 0. 9 is 16th to the first. B is 16th to the squared, 2 is 16th to the third, and then you add all of those together to get the value. But when we're thinking about it as an address, the bytes in a little endian system, which the GBA is, we actually switch them around in order of which one is the least significant byte. It comes first in a little endian system. So there's little endian, then there's big endian. Big endian is kind of how we're thinking about it when we're writing our values. You know, when we write 123, 1 is the most significant number. 100 is the most significant number in 123. And we write that first, and then 20 is more significant, so we write it second, and then 3 is the least significant. But in a big endian system, it would be 3, 2, 1 if we were splitting it up, like, you know, in the tens place. But we're not splitting it up in the individual place. We're not completely flipping it. We're splitting it up at the byte, which a byte is 2 4-bit values, so it is 2 hexadecimal places. So at the byte value, we are splitting this up from 2B93 into 93 2B, because 93 is the least significant byte, 2B is the most significant byte, So 93 comes first in little endian, and 2b comes second. And I know that can get a little confusing, but a lot of the time, unless you're doing really complicated stuff, you're not going to have to actually worry about the fact that the endianness is, not the same as what you might be thinking. Don't worry too much about it, but that is how it works. I think that covers the majority of what I wanted to talk about in this basic binary tutorial. There's obviously a lot more to talk about in a topic this complicated, especially with memory addresses and how we store our data, but we will get into plenty of that later. We'll also talk about, compact structs and how we can actually, those are things that are commonly used in pokeemerald to store data, and how we can access the extra bits of said structs that are unused. But for now, I think that's going to be it. We're going to wrap up this video. If you have any comments, if something was wrong, if I skipped over something, if I rushed over something and, made a mistake, let me know. Otherwise, we will see you on the next one.